In this video, we're going to again look at this whole idea of displacement, velocity, and acceleration using calculus. So again, if I just write out our displacement, our velocity, and our acceleration, hopefully you'll recall that as we go from displacement to velocity to acceleration, we take the derivative with respect to time, and as we go up from acceleration to velocity to displacement, we are taking the integral with respect to time. Now, I want to look at some graphs real quick, and with respect to this integral idea and derivative idea, just so that we can make sure we understand what's going on. So let's say that we have a graph of and let's say this is the displacement as a function of time, and then this is just the time. And then let's say that this graph down here, and so I'll draw that. So let's say the graph is like this. X equals t squared. Alright, now a graph of the velocity would look like the following. So remember, to go from displacement to velocity, we take the derivative with respect to time. So we could say, alright, v equals 2t. So that would be a straight line. And actually, I've added a little space there, so that graph isn't completely accurate, but v equals 2t, a straight line. And then for acceleration, a of t would just be this line, a equals 2. So a line with a slope of 0. Now, what happens as we go from this graph to this graph to this graph? Well, the velocity is equal to the change in x dx over dt, right? So I'll put in parentheses equals dx over dt. Now, this is the slope of the displacement curve. So the slope here is 0. Slope is 0. Hence, this point here is 0. The slope here is, let's say, positive 1. So this point here is at positive 1. The slope here is it's steeper and positive. It's, let's say, positive 2, twice as steep. This we would plot as 2. In the same way, from velocity to acceleration, the slope of this velocity curve we can see is constant. It's 2. Hence, the values for the acceleration will be that slope, 2. Now, in terms of integrals, the area under this acceleration curve gives us the velocity, and the area under the velocity curve gives us the displacement. And we're going to use that really quick just to review. Hopefully you haven't forgotten the constant acceleration equations, but just to review, I'm going to draw a graph of acceleration with respect to time, and we're going to practice actually applying what we just, I'm going to do a velocity. Let me undo that. I'm going to graph velocity with respect to time, and we're going to remember that if we take the integral of velocity with respect to time, so the integral of velocity with respect to time equals what? Well, according to what we've written up here, the integral of velocity with respect to time equals the displacement as a function of time. So this is my velocity graph, and I'm going to take the area underneath this, but I'm going to break it up. This is constant acceleration. The slope of the velocity is some constant number. I'm going to break this up into two shapes. And actually, this is going to be more algebra than calculus, but what's the integral of this? The integral is the area, and the area under this curve is simply the area of this guy plus the area of this guy. And so so this is velocity initial. We start off with one velocity. We end up with velocity final. And the area of the triangle, so for this integral, the area of the triangle is 1/2 base times height. So 1/2, the base is just this amount of time. So we'll just say t. And then the height, what's the height of this? Well, the height is velocity final minus velocity initial. So velocity final minus velocity initial, 1/2 times velocity final minus velocity initial, and then plus, now this area of the rectangle below is just base times height. So the base again is that time elapsed, maybe it's 3 seconds, so time times the height, which is constant, velocity initial. That whole thing equals the displacement, however far we moved. Now, if I just scroll down here, we will be able to see that this, with a little bit of rearranging, this will boil down to one of our constant acceleration formulas. So let's write out what we have here. Or before we write out what we have, I want to do one small change. What's acceleration equal to? Acceleration equals velocity final minus velocity initial over time. So if we say acceleration times time, that's equal to velocity final, and this is just out of the definition of acceleration and the definition of acceleration that we learned way back at the beginning. If you're accelerating at 20 miles an hour, that means that's how fast, or 20 miles per hour squared, I guess it would be. That means that every hour your velocity is changing by that 20 miles per hour squared. Usually we do meters per second squared, but so a times t equals velocity final minus velocity initial. So let's plug that in here. 1/2 times time times acceleration times time plus time times velocity initial equals the displacement. Simplifying this, we'll just switch the sides around and hopefully you'll recognize this. Displacement equals time times velocity initial plus 1/2 at squared. Now this ended up being more algebraic than actual calculus, but what we did here, we took the integral of this and it ended up being, because of our constant acceleration, it ended up being just the area of a triangle and the area of a rectangle. But I hope you see, we're using the concepts of calculus here with the constraint of constant acceleration in our justification of this equation. In the next videos we'll continue to explore this concept of using calculus with displacement, velocity, and acceleration a little more.